ナムラの方から、英語がいいんだっけ。Today I will present about the overview of logic design flow. This is basically logic design flow, so I think it's very simple, so you can understand. First, I would like to introduce myself. Okay, my name is Ken Amura, and I was born 1969, December. So I'm almost, I'm 47 years old. I was born at Mie Prefecture, Yokkaichi, maybe. You know the Yokkaichi? Oh. Okay, so next slide, I will show you the place of Yokkaichi. And I have 2 brothers and 1 sister. And also, I already married. So I have a son and a daughter. And my son is 22 years old. So last spring, he graduated the university and joined some company. I don't know the detail. And my daughter is just joined the university. She is about 18, so she's very difficult for me. It's same. Okay. Next page is Yokkaichi. Yokkaichi is here. It's close to the Nagoya. It takes 40 minutes by train from Nagoya. And Yokkaichi is there are many combinat, many factories. So, and also, Yokkaichi, we have Toshiba factory. From my parents' home, I can see this building from my home. It's close to my home. So it takes just half hour by bicycle. Very close. So this is my hometown. And I graduated Nagoya University, occupied physics, and I joined the previous company at 1992, and I worked for I worked for there 24 years, almost quarter century. Previous company has some celebrate anniversary of the when we work for the company about 25 years. Then they say the company celebrates that, and they will give 1 month vacation to celebrate. So, but before 1 year, I moved to the preferred networks. I just joined this company last January. So I'm new for this company. So anyway, okay, this is my introduction. And about the previous company, I joined some department group. That group mainly focus on the EDA to EDM in electrical design automation. These two are used for the logic design. And the department maintained these EDA tools, and also they the department maintained the workstation and for the hardware design in logic design. These two work on the host system. It's almost 25 years, so at that time, we use the host system to design the logic. And also, some of workstation data at that time. We have RS6000, so we have Solaris SunSpark to design. And also the department support does not have our own product. The department support to design some ASICs for other departments. Okay, so next is about. So first, I would like to explain about the logic design flow. This is basically quite basic flow. Here is RTL. RTL is register transfer level description. Usually we use VHDL or Verilog HDL language to describe. And then we compile the HDL code. We call it a synthesis, logic synthesis. Then we will get the netlist. I will show you about the netlist. And after we get the netlist, we pass it to the layout tool, layout and the placement and router tool. That to process the netlist, and it makes an actual layout for the chip. So after the this layout and the router tool, we get the layouted netlist and the GDS and the left def. This is mask information. Actual geometry information is hard. This is roughly very simple overflow of the logic design. And I focus, in previous company, I mainly focus on these two, logic synthesis and simulation, mean verify the function of the HDL. Here is a very short example of the HDL. Actually, this is a Verilog HDL, and it looks similar to the C language. It looks. We can use if else or something. It's almost same, but big difference is okay. In this statement, process sequentially as a software, but we have this kind of these two blocks work in parallel. That is a big difference from the software. So the debugging HDL is slightly different from debugging C code. Then function verification is to verify the function. So we have some module, and we gave some stimulus to this module. Then we get some result from the module, and we check it is expected value or not. That is function simulation. Usually we use Verilog or HDL code to describe the test input stimulus, and also describe expected value. Okay. Then when we finish to write its RTL code, we will do the compile logic synthesis. Then we will get this kind of netlist. Netlist has this one is a Verilog format netlist. Actually, this netlist represents this kind of the logic. And netlist has these blocks and the wires and it will represent a connection for each block. And this block we call gate or cell. We call this kind of cell block called cell or gate. Okay. Especially this rectangle one is maybe some guy know that this one is we call the D flip-flop. This represents a memory element in the logic, and this one is and gate. Okay, so this netlist represents this logic. This is the result of the logic synthesizer. And okay, actually, these cells are designed before the logic synthesis. I mean, to compile the RTL, we need a technology cell library. This library represents NAND gate characteristic or DFF characteristics. So these libraries are designed by the different teams. Here is the process development overview. Overview. First, we developed some technology node. At that time, first we define the process. So we check the characteristic of transistor or such things. We define the process. Then, with such information, we do a cell level design. I mean, for instance, here is an inverter. We make this inverter with two transistors. And these transistor characteristics depend on the process. Okay, so in after process development, we will do a library development. Library means we will develop like this kind of cell. We will design the many cell libraries. I mean, inverter or NAND or flip-flop, many cells are designed. These cells information is used here as an input of the logic synthesis. So with RTL and the technology library, we can get netlist by the compiler. Okay. So usually we do not use a transistor level. We do not do a transistor level design because we have a cell library. We just represent the RTL code, and the logic synthesizer compile it into the RTL netlist. The netlist have many cell and gate. But sometimes if we need some special circuit, analog circuit, or we need some high performance circuit, in that case we use we do a transistor level design, not like HDL. We describe the SPICE netlist and verify the function of the netlist. So there are two types of design. Easy one is use RTL and compile it and get the netlist. The other one is use a SPICE and the transistor model to describe the logic. So so that means if when we do a spice level design, we can get a more powerful logic. I mean, if the usual RTL design work 100 gigahertz like that, in that case, maybe we can get more. I mean, 2 gigahertz or 3 gigahertz logic with spice transistor design. And also we can reduce the size of the design using the spice netlist transistor level. Okay, so when we get the gate level netlist, we will gate level netlist simulation. It's same as a function simulation, but we targeted the actual netlist. With this simulation, we will have delay information for each cell. Each cell has some delay or such information. So this simulation result is very close to the actual hardware behavior. Then we will place and loop. And then it's almost same, but each cell are placed to some specific place. And that means some wire has, some block placed very far from other one. It might, the wire has so long. In that case, the wire cause some delay to propagate. So with the layout netlist, we can do a more accuracy simulation. It's much more behavior is much same as real one. So we do a layout netlist simulation to verify the function. So logic designer do a simulation, describe RTL to represent some function and verify the function with simulation. And then he compile the RTL and get the netlist. And with netlist, we can do some delay simulation to check the function. After then it works fine. Then we will do a place and loop to place each cells. After that, we will get a layouted netlist. This contains the more accurate actual delay and some characteristic of the netlist. With this netlist, we can do the same verification, and the result is much closer to the real chip. So this is an overview of the logic design process. Okay. Next is about a project I supported at the beginning of the previous company. The ASIC is for the PCM-CIA controller, PCM-CIA interface. I think not so many PC does not have some PC has such an interface, but in these days there is no such an interface. Anyway, we have such ASICs that is on some notebook, and this design was done by this design was described only netlist. We do not have any RTL information. At that time, we do not have any logic synthesizer or compiler, so we describe the design by the netlist. So I think the netlist format is EDIF is a standard format to describe netlist. And that project is convert the netlist into some other process, because we want to reduce the cost of the fab. So we want to move to our own fabrication to the other third vendor fabrication. So we convert the netlist to the third-party technology. So this is simple image of the process. There is an original netlist, and I just replace the gate to the target technology and do the layout. At that time, it's very hard for me because the source code is just netlist, so there is no higher level description. So debugging is so hard. And also, I did a simulation to verify the netlist. And also when I get converted the netlist, I gave it to the third vendor to lay out the netlist. Then they give back they give back layouted netlist to me. Then I did a simulation with layouted data that have some delay information. But at that time, I had many timing violation, and it's very hard to converge the timing problem because of the main reason I had so difficult to converge is that design is not a synchronized design. I mean, this is very simple one. This logic works only with one clock. Here is the clock. And these four rectangles is a memory element, and it works with clock. This is a synchronous design, and in the project, the design was not synchronized design. That means some output connect to the clock signal, so it makes so difficult to converge the timing. So in these days, almost design use synchronized design because it's easy to manage the timing closure. But at 20 years more ago, some design have such a tricky logic, and it use non-synchronized design, and it's quite difficult to do a timing closure. Okay, so this is the first project I joined. The first project I joined to the previous company. Okay, after that, I will go to the US to study about the EDA2. I mean, logic synthesizer, such a tool developed by our company. At that time, many company has its own in-house tool to the synthesize or simulation. Such a tool owned by each company. But in these days, Synopsys or Cadence or such a company provide us cheap tool. So almost company did not have own in-house tool in these days. But at the time, 20 years ago, our company had such a tool, in-house tool. So I went to the Burlington, Vermont in US. It's here. It's very close to New York. At that time, actually, this is the first trip to abroad for me. And also, this is the first time to ride on the airplane at the time. So from Narita to Burlington, we have two tranches. First, I arrived to Chicago, and the next is Chicago to Boston, and then go to the Burlington. Before I went to there, I heard from my colleague, the Burlington is so local place, so it's not town, so its its local place. So I imagine the airport is small, such as things. But actually, when I arrived to the airport, it's so big, and it's big, so big city. So I surprised the United is so big. So even if local city, but the airport is still big. But when I arrived to the Burlington, I mean, actually, I did not arrive to the Burlington. I was waiting my baggage at the airport, but 1 or 2 hours, but the baggage was not out. So I was asked to baggage claim counter, where is my baggage? Then she said, you arrived at different place of the Burlington. So actually, I arrived to Philadelphia. So I made that wrong. I arrived at wrong place. So when I changed transit at the Boston, before get off the airplane, I hear the announce about the next transit, and the announce say I had to go to gate 15 or such a thing. So I went to the gate 15 and wait for the airplane. And actually, I don't know I did not know how to check my flight. There are many displays that display show the departure time or flight arrival time. But actually, at that time, I did not know what that is. So when I waited to the next airplane at the gate 15, and some airplane come, and attendants announced us to ride on. Then I got into the wrong airplane. At that time, we do not have any checking machine. The attendants checked my ticket and break it. So she did not check my flight number or such a thing. So I went to the from Boston to Philadelphia. So this is very hard for me, but I could study how to see the how the display meaning. So I will never fail again. So I took this story to my colleague. Every colleague laughed me. You are so strange. Almost people cannot do such a things, but I did it. And also I learned about from Philadelphia to Burlington. I need to take more. I need to take 2 more airplanes to ride on the airplane, but I don't need to pay any additional fee. So it's lucky for me. Okay, so this is strange. Okay, next is about another project that is called Grep 6. Grep 6 is fixed hardware pipeline, has a fixed hardware pipeline to calculate gravity. That, and this is special for the gravity calculation. It does not do any other calculation. It's just only for that. So, but the tip, we can get some gold Nobel Prize because of the performance and such a things. So at that time, I worked for the Makino Sensei and Fushige Sensei. They were the belong to the Tokyo University. And also at that time, we have another project, MD Grade 2. That is the same kind of the hardware, but this hardware is for the molecular dynamics. So this chip designed by the Liken. As I said, we have two projects. One project is grade 6, the other is MD grade 2. And about the MD grade 6, the project has does not have enough money. So we have to reduce the cost. So we have not so many we do not have not so many engineers, and also we have to use some third vendor fabrication. But about the MD grade 2 has much money, so we can use some famous fabrication to make a chip. At the time, I worked for Kobayashi-san, maybe someone. Kobayashi-san is famous about logic design, and he had some lecture. He has some class at the Tokyo University. So Kobayashi-san support the MD grade 2 because they have much money, so they can pay for the professional. But in constant grade 6 doesn't have enough money, so I and Makino Sensei and Fushige-san, just 3 people is designed for this project. And yeah, project is both well, but when the chip is from the factory, then we put the chip on the board and evaluate the chip. We have some problem about the power dissipation. The chip has many calculation engine, so it wastes much power during the calculation. When the chip does not calculate, in that case, power is not much smaller. But when it starts to calculate the gravity, then the power waste going too high. And that causes IR drop in the chip waste power. That means we need a bigger current from VDD to ground. That causes IR drop in voltage is going down because of the resistance of the VDD plate. So when we will make some chip, we will have some trouble. It's always, but this is not for functional trouble. This is because of the fabrication problem. So I asked the third party to fix this IR drop problem. They will add additional ground and VDD to solve to reduce the register of the VDD and ground signals. Okay, so this one is next project I joined. After this project, I will do some about design for test DFT related. DFT is design for test. Actually, we make some chip. We need to test the chip made correct or not. So very old day, we use a function pattern to verify the chip correctness. But so if the logic is so simple, we can cover the whole chip with a function pattern. But the logic size become much bigger. In that case, we cannot cover with a function pattern. So we will implement some circuit for the test. That's called the design for test. Basically, we connect every memory element into the one single chain. That with this chain, we can control the every memory element inside ASIC, inside chip. So when we want to test some code here, then in that case, we set some specific value to each register. Then observe the value. Then we can check this port is break or broken, or we can detect the defect of each port. So scan chain is a basic idea to check the logic correctness, to detect defect inside the chip. So I did such things after the Graph 6 project. And in these days, the logic size become much bigger and bigger. And we cannot, that means scan chain lengths become more longer. That means we need time to load the data into a chain. It takes a very long time. So that means the test cost become much higher. So in these days, not these days, it's almost 10 years ago, we divide the scan chain into the small part of chain. And the input of each chain is from a PRPG, should random pattern generator. It generates some pattern, and the value is going to that scan chain. And then check the result of the chain output into the linear LFSR, linear feedback shift register. Then we compare the result is expected. So with this logic, we can reduce. We do not provide any test pattern for the chip. We just turn on the chip, then this logic works by itself, and it detects the defect inside the chip. So I did this kind of things after the Graph 6 project. And also I did some logic diagnostics for the chip. As I said, with the scan chain, we can detect the defect inside of the chip. So in the publication, we have many chips. Each chip are tested by the scan chain, and some chips fail because of some defect. So we have many chips. We can get many chips from the one warehouse, and we test every chip. Then we get every result for the chip, and we summarize this failure information. Then, if the defect is randomly, in that case, the failure also random. But sometimes the process have some trouble, or maybe the design have some trouble, some difficult part. It has some difficult part. In that case, the failure is not random. Slightly, how do I say? ちょっと偏った結果になることがあります。So logic diagnostic means we grab the very big data. I mean, if the chip make 1,000 or more. Then we get many failure data. We analyze it, where is the defect point. And then we look when the defect is some local, not random. In that case, some design has some weak, or we can get such information from the logic diagnostic. So I did such things at that time, and the information makes better yield when we feedback the process guy about this information. The process guy control the change some parameter for the fabrication. Then it makes better yield they can get. So this one is about logic diagram. After that, I will do another great project, great app. This one is a more generalized project. It's not only for the gravity. It's a more kind of processor, SIMD processor. And I work for the hierarchy sensor and the Makino sensor also. And also at that time, I worked with Nishikawa-san. He is president of this company. He did he made some compiler for the chip. So at the time, this is the first time I met Nishikawa-san, but actually I did not remember it. He's just a student, so. Okay, so this one is not get the project. I think we get second place for the green 500. So I think top is IBM Blue Gene or such a PC, but we placed the second one. So, and IBM has much resource to develop, but in our case, we just about 5 or 6 engineers to develop. So it's more cost efficiency to develop. Anyway, we can get such a price at that time. Okay, so I joined some other project, but I think I cannot say about this project because that is owned by the previous company. So that's all for my introduction and very basic design flow about ASIC. That's all. Thanks.